Here's a circuit, the same circuit I looked at before, assuming sinusoidal steady state. We're asked to find the current IS and then the voltages across the respective elements. So our first step will be to transform the circuit to the phasor domain. Okay, so that's sort of the overview of our transformation. Our voltage has to become a phasor quantity. Our elements have to become impedances, and our voltages across the elements, because we'll be in the phasor domain, also are going to be phasors. So everything has a hat. The hat indicates that we're dealing with complex quantities. Also, it's customary to have our phasors be capital letters as well as our impedances. So let's write out our phasors as numbers along with the impedances. From the problem statement, it's fairly straightforward to write down the voltage phasor. That's in polar form. One thing you'll notice is that there are these omegas in there just to remind us that these are functions of frequency. We may often just get lazy and forget to write the omega, and that's fine. We'll recall here that ZR is just R. First off, we need to know what omega is. We can see from our voltage that F is 600 hertz, and so we know what this is. It's that many radians per second. So when I do that math, I get this impedance. When I do this math, I get... So we've now transformed everything that we can to the phasor domain. Now let's do some analysis. We'll define our phasor current, and we can get that using Ohm's law, right? So the total impedance is as follows. Because these are all in series, we just add them up. And I'm not going to worry about doing these. We'll go to MATLAB here in a moment and do that and get these numbers. But we can get the source current. That's just coming from Ohm's law. And then, once we have the source current, we can easily get the phasor voltage across each element. So that will be like this. And once we have those, it will be straightforward to convert them to sinusoids. So let's now turn to MATLAB and we'll crunch these numbers. Some of them I've already crunched sort of behind the scenes, but let's do this anyway. To do this, I'm going to get a new live script. We'll call it series RLC example. We'll start by putting in problem parameters. These are the values given in the problem. And now we have a description of the source. You'll see in the sidebar that I made a couple of tools, polar to complex and display complex. Let me just show you, for example, what they do. So I can use polar to complex to enter something in polar and it makes a complex number. So let's just try this, for example. First, what I do is I enter the magnitude. So I'll try 1, and let's do an angle of 0. And so this spits out 1. Let's just sketch this on my iPad screen really quick. So here's my real and imaginary axes. So if we go over 1, all right, this is 1, 0. That's just the 1. That's exactly what we're looking at. The angle is 0 because it's relative to the real axis. So it's just 1. Let's do another one. If we were to put in 2 at an angle of 45 degrees, well, we'd have a vector of length 2, and this angle is 45 degrees. So you should expect to see 2 root 2 for the real part, and then imaginary 2 root 2. So let's just try that. And there it is, real part and imaginary part. So that's what this polar to complex does. So I'm going to use it as we transform our circuit to the phasor domain. As we saw earlier, the angular frequency is important, so let's do this. And now we can calculate things like the impedances. So in MATLAB, 1i is the complex number. I have a negative sign because that's the formula for capacitive impedance. I'm using W for omega. And I can run this just to make sure everything works. That's my capacitive impedance as we saw before. I'll use display complex, just it does it a little bit nicer. This will tell you the magnitude and angle also. Again, that's a program that I wrote, so polar to complex and display complex are proprietary, if you will. They're not too bad, you could write them yourself. That's our capacitive impedance. We can do the same thing for the inductor. And if you feel like it, you can do ZR. Or just use R, that's fine. You can see these are numbers that I got before. And notice what I'm doing here. This makes it easy. I'm doing it in MATLAB. Notice I'm using variables. I'm putting my complex numbers in variables. So often as a student, you may not get to use MATLAB in tests, so you have to make sure you're proficient with your calculator. And if you have a calculator like the TI-89, for example, they're very good at doing variables and mathematical expressions. So use variables heavily. It reduces the opportunities for mistakes because you don't have to enter these complex numbers over and over again. So I recommend heavy use of variables. Now we can do some analysis. Let's make these sections. So this section here will be transformed to the phasor domain, and then we have our analysis. So let's get a total impedance. That Vs actually should be up here in the transformation to the phasor domain. And we'll display it. Okay. Now we can get the source current. Just run that to make sure it works. Let's just write out our total impedance. So over on my notes, I'll write here that my total impedance looks like this. All right, so now we have a value for the total current. You can write the phasor voltage, right, which is 1 volt angle 30 degrees, divided by total impedance. And let's see if that makes sense. The number that we got for IS here is 0.038, angle 47.07. I say that makes sense because, right, it's the top angle minus the bottom angle, so 30 minus negative 17 is 47. Units are amps, so if you like, it's 38 milliamps. All right, so now we can get the voltage across the various elements. Let's just do this all at once. Okay, so now we can make MATLAB display the various voltages. You know what, let's make this bigger. So VR, using our formula, I have to make it smaller. VR. Okay, so I have values now for VC, VL, and VR. One thing we'd like to do is to check, do they make sense? They should satisfy the Kirchhoff's voltage law equation. And if this goes well, this KVL check should be 0. So we run this, and what you see here is it's 0 plus j times something to the negative 17. Well, that something to the 10 to the negative 17 is very, very small, so we might as well call that 0. So we should be happy, confident that our KVL is satisfied. We have good values for the resistor voltage, inductor voltage, and capacitor voltage. The other thing I'm not going to show you here, but as an aside, voltage division could have worked also, because you'll see what we did here is exactly voltage division. So that's how you would calculate it doing voltage division if you wanted. Exactly equivalent. So we're not going to do those numbers. So we have now the phasor versions of everything we were looking for, and we can transform them back to the time domain. So those are the time domain voltages, and let's do the time domain current. There are a few things I want to point out with this result. First, notice that even though the source voltage has a magnitude of 1, it's quite possible that through the wave mechanics of the voltages in the circuits, it's possible to get an element voltage that has a larger magnitude, which can be surprising. Another thing to point out is that notice that the resistor voltage has the same phase angle as the source current. That should be because the resistor has no imaginary component. Its current and its voltage are in phase. However, for the inductor and the capacitor, their voltage is not in phase with the current. Rather, it has some delay or advance, and we'll see that here in a moment. In fact, for your sake, I'm just going to plot these in MATLAB. So you may or may not want to fuss with MATLAB. You're not often going to be asked to visualize these things, but if you want to, MATLAB is good. So let's construct the time-varying waveforms. So since phasors get capital letters, back in the frequency or the time domain, we'll use lowercase letters. So I'm basically just converting my phasor back to a sinusoid. I'm going to recall that angle gives me an angle in radians. So that's what I want, because cosine uses radians. I need to define a t vector, so let's do that, for example. So start with a period t. You know that relationship, that period is 1 over frequency. Let's make a time vector. And I like using variables. It makes things easier to change later if I want, rather than hard coding numbers in. So that should be enough. We have t, we have omega, that's our 2 pi t times f. Phase angle, let's do the same thing for the capacitor and the inductor. So abs gets us the magnitude, angle gets us the angle. Let's just try that. For example, let's see this. Right, so if we take the abs of VR, you should see that's the 0.95, yep, okay, and then angle, VR, it's 0.8215, is that 47.07? Let's try it again, multiply by 180, divide by pi, and yep, that's how that works. So we should be confident we have a good voltage for the various elements. Let's do the current. Here's our plot. Let's make it better. So make a better font, turn on the grid, bigger font. Okay, so we need plots. Every good plot has axes labels with units. Interpreter LaTeX gets me fancy math typesetting, so I have this italicized T. S is not italicized because it's not in the dollar signs. And we need a legend. That didn't turn out so well. I need to put interpreter, a tech in there. Okay, so that's looking nice. Let's notice some things here. This resistance peak happens a little bit before the capacitance peak. And you can see in my results here that the R has a 47.07. So it's advanced some. And then the yellow line, the capacitance, it has a negative 42, so it's delayed. So we should expect that the peaks of the resistor happen a little bit before the peaks of the capacitance, and we can quantify that. Let's run this. It'll get us a value in radians. You can see that. So let's turn it to degrees. So the capacitance is 90 degrees behind the resistance, and we should expect that because the resistance is in phase with the current. In fact, I'll show that to you. Let's use subplots. So subplot 2, 1, 1 makes a 2 by 1 array of plots, and it addresses the first plot. So in the first plot, we'll just copy and paste this, and we'll plot I, S of t. Copy and paste. Run that. Well, it made the second plot smaller. I'm going to go back to not subplots. We can afford it. We have the room. We need to put here figure so that the first plot doesn't get replaced by the second plot. So there's our current on top, and there's our voltage on bottom. Oh, let's do figure here also. Run that. It'll be better. Notice here, let's make that bigger. Notice that the peaks in current align with the peaks in the resistor voltage. So again, the current in the resistor is in phase with the voltage of the resistor, but the capacitor current is slightly delayed behind its current, right? Because they all have the same current. So let's put here IS, in fact, and let's run that again. So now it says IS. So the current drives the same waveform in the resistor, but a little bit smaller. And then it drives a delayed waveform through the capacitance. It actually drives an advanced waveform in the inductance. So, for example, we'll take the delay between the inductor and the current. We can do that. And relative to the current, the inductor voltage is 90 degrees ahead. And can we see that? Well, here's the inductor voltage. Notice that its peak is a bit ahead of the current peak. Let's see this again. I'm going to show you one last way to plot things that makes it really nice. Instead of using time, I'm going to unitless time. So copy paste. Here we do time divided by t. That's the period. So we scale everything to t, big T. And in the x label, put t divided by t. It's unitless, so we get rid of the seconds. Let's run that, see how that goes. Oh, I need to do it for this one too. Let's get rid of the units. Okay, so this time from 0 to down here, 0 to 1, that's one full period. You can see that in the waveform, right? Like it goes from here to there. That's one full period. And now you can start to see things a little bit better because your mind doesn't have to deal with those wonky units in milliseconds. So it can be advantageous to plot in a unitless manner so you can see what's happening in one period. So again, the inductor voltage leads the resistor voltage. The resistor voltage is in phase with the current through all of them. So the inductor leads, the capacitance, the capacitive voltage lags behind the current that flows through all of them. Okay, so that is kind of what I wanted you to see. I want you to start to have an understanding of what these phase angles mean. Phases are all relative, right? It means that we're comparing something to something else. In this case, everything is relative to a sinusoid, actually a cosine, that has its peak at time 0. So imagine a cosine peaking at time 0. That's the reference. And the resistor voltage has a positive angle because it's advanced. It happens just before that peak at 0. The inductor voltage has a bigger angle, and so it happens quite a bit before the peak of the reference cosine at time 0. And the capacitor has a negative phase angle, which means it's going to be delayed. It's going to happen after the reference cosine at time 0. And we can even put that in. Notice this purple sinusoid now is our reference sinusoid. It peaks at 0. The resistor voltage leads it, inductor voltage leads it, capacitor voltage lags it. And then, of course, you can find how much any of these two lead or lag one another by subtracting their phase angles, like I showed you earlier. Okay, so I hope that gives you a little bit of a feel for how we do this, right? We start with a circuit in the time domain. We transform it to the phasor domain. We do analysis without any differential equations. The trade-off is that we have to use complex numbers. And then we transform back to the time domain so we can see what's going on in real time in AC steady state. Of course, I did this for a series RLC circuit. You can do any circuit with this. Things could be in parallel, parts of the circuit can be in series. You just apply all the rules that you've already been taught and you use them in the phasor domain, and that's fine. No differential equations. Remember to like the video, leave comments, subscribe to the channel. Have a great day.